welcome to tonight's IARAI fireside chat. My name is David Kreil. I'm one of the scientific directors of the Institute of Advanced Research in Artificial Intelligence in Vienna, and it's my great honor to host tonight's session for you. I'm particularly delighted to welcome Krzysztof Choromanski of Google Research, a well-known, highly cited researcher in machine learning. He works at Google Brain Robotics in New York and Columbia University, and he's the first author of the groundbreaking Rethinking Attention with Performance paper. He's joined by our very own Sepp Hochreiter, who really needs no introduction. You all know him as the leading pioneer of artificial intelligence. He was the first to identify the key obstacle to deep learning and then discovered a general approach to address this challenge, and thus became the founding father of modern deep learning and AI. In recent work, he has revolutionized the efficiency of reinforcement learning, and now he has analyzed the latest ambition model architectures, including the highly successful transformers, as well as the performers, their smarter younger brother, you could say, linking their attention mechanisms to update rules of novel modern Hopfield networks, yielded novel insights and opened many exciting avenues for future research. Today, we're delighted to welcome them and Johannes Brandstetter and Hubert Ramsauer from his team to discuss the impacts of this work and the many opportunities that it creates in the field. Thank you so much, and the floor is yours.
David, thanks a lot. I'm humbled by this kind introduction. It was very nice. I will go ahead and start my presentation. I'm talking about modern Hopfield networks. Here in this slide, you see on the right-hand side, deep learning architecture. It's here a deep neural network. And our idea is to equip this deep neural networks with memories, with associative memories. Which you see here now on the right-hand side, where this deep neural networks are equipped by a memory, where each layer gets an additional memory. And we believe that this new kind of architectures push deep learning beyond convolutional neural networks or recurrent neural networks. We can build new architectures with higher performance than previous ones. Our idea is to use these modern Hopfield networks, I'm coming to this, and embed them in layers of deep learning architectures. This means integrating associative memories into deep learning. This allows us to do association of sets, pattern search in sets, pooling operations. We can also create memories like known from LSTMs or GRUs. We can learn prototypes. We also can implement the transformer attention mechanisms. We can implement sequence-to-sequence learning. We can process point sets. We can do multiple instance learning. And we can also implement by these memories k-nearest neighbors, support vector machines, or learning vector quantization. All these kind of things are possible. Modern Hopfield networks. Modern Hopfield networks were pioneered by Krzysztof and Hopfield himself. It's the same Hopfield who did in the 80s as classical Hopfield networks by paper in NeurIPS in 2016, and also by Demircigil in 2017, which built on the paper of Krzysztof and Hopfield. And these modern Hopfield networks tremendously increase the storage capacity in contrast to the classical Hopfield networks. And another property is they converge extremely fast. Standard Hopfield networks are all things, they go back to the 60s and 70s, and now nobody remembers them anymore, but now perhaps they come again. And the Hopfield networks were popularized by John Hopfield in 1982. Here, an example, it's a bottom row, we have standard binary Hopfield network, the classical Hopfield network. Some patterns are stored, and you see it's the Simpsons, Homer so half of the image is masked out. And you cannot retrieve this image because all these images were highly correlated or overlapping. If you do it with a modern binary Hopfield network, you have the same retrieval of the same masked out image, but now it works. And this is due to the high storage capacities of this. But as I said, we want to integrate this new Hopfield networks into deep learning architectures. But these new achievements are still binary Hopfield networks. But what we want to have is differentiably Hopfield networks, differentiably associative memories, because we want to still use backpropagation. We want to use gradient descent. We need the gradient of this stuff. Therefore, we need something like continuous Hopfield networks. Also, one goal is that we want to keep this retrieval with one update, because if you can retrieve with one update, we have the same as an activation of a layer of a deep neural network. Whether it's a retrieval or whether it's an activation of one layer is the same in this case. Therefore, retrieval with one update is the other goal we want to achieve. And of course, we want to keep the high storage capacity of these modern Hopfield networks. Therefore, we propose a new energy function and a new update rule. The new energy function is at the top. I don't go into it. It keeps exponential storage capacity and also the retrieval of after one update. This is inherited from this modern binary Hopfield networks. Here we have an energy function for a continuous Hopfield network. And also we propose a new update rule, which is given in the bottom row. And this update rule has some properties. First of all, if we iteratively apply this update rule, we can guarantee that the update converges to a minimum. Also, saddle points would be possible, but minimum is much more likely to be found. Still, we have this storage capacity. We have exponentially large storage capacity, exponentially in the dimension D, in the dimension of the patterns, in the dimension where the patterns live, the stored patterns. We also have retrieval with one update, which means if we do one update of the update rule, we are epsilon close to the fixed point. And epsilon is very small. We see it, this here is a retrieval error, this epsilon is exponentially small. If the pattern is well separated from the other patterns, if it's not overlying. Therefore, we have now a continuous Hopfield networks, high storage capacity, and retrieval with one update. Therefore, we can readily implement it into deep neural networks, because now retrieval and update of a layer is the same. Here an example, we have here many images. Now you see the grayscale. This is a continuous values now. You have this continuous valued images. And now if you want to retrieve an image, which half of the image is masked out, it can be done. These modern Hopfield networks work and have similar properties like their binary counterparts. And now the interesting fact is here that the new update rule is the same as the transformer attention mechanism. We see this here, it's a bottom rule. This is the Hopfield energy function for the binary modern Hopfield network of Krotov. Here we have the new energy function. It's our energy function, sets the new update rule corresponding to this new energy function. And now if we compare this update rule with the transformer, we see similarities. And if we closely look into it, we can really map it one-to-one if we do some kind of embedding of this X space into the Hopfield space. Now we have this new energy function. It allows us to create Hopfield networks, continuous valued modern Hopfield networks. But now we have design choices. And the choices are what patterns we want to store here. There are different possibilities to do that. And where the queries come from. We know from transformer what the transformer is doing. It's storing queries from the previous layer. It's storing patterns from the previous layer. It also uses queries from previous layer. But there are more possibilities. Here, the first layer, we have call it different layers. There's a layer Hopfield, there's a layer Hopfield pooling, and there's a layer Hopfield layer, which are PyTorch implementations. The first one is known from the transformer, where we have here the stored patterns. In transformers are called keys. We have this R, this are the queries, and you put them both into a layer, and you get something out. That's the transformer attention. You can build the transformer attention. But what's also possible is that you only fill these layers with some keys, but the queries are learned. They don't come from the previous layer. And here now you can do something like multiple instance learning, where the data set is always put into each layer, and you can always query the data set. The data set is an object consisting of different instances. Or you can fill it with sequences. If you think about LSTM screws, you can always fill this memory with your original time series and always probe it, always do different queries on it. Here's another possibility, the Hopfield layer. Here we propagate the queries from layer to layer. And now it's up to us with what we fill the memory. So memory could be filled with the raw data. If it's the raw data, we can implement something like support vector machines, where some stored patterns serve as support vectors. We can do k-nearest neighbor search, where the softmax is looking for the nearest neighbor. We can do a learning vector quantization, where we find specific prototypes, where we base our property on it. And here you see there's a plethora of new architectures, new ideas. It's your design choice. What do I want to store? Does it come from the previous layer? Does it come from the input? You also can store databases. You can store prototypes. You can even store, perhaps you don't want to learn your whole data set. You don't put your data set into the weights, but perhaps some data points you cannot learn because they are too hard to learn. You just memorize it. You put it into memory. You memorize the outliers, the exceptional cases. All this is kind of possible. We didn't explore everything, but there's a huge field now open where we can explore these architectures. Thank you. That's from my side.
Thank you so much, Sepp. Krzysztof, would you be happy to complement this with your perspective?
Thank you so much. And at the beginning, I would like to thank for the invitation by the Institute. It's really great to be here. And yeah, let me give a short presentation about performance right now, and then we can see some connections between both lines of work. My name is Krzysztof Choromanski. I'm in Google Brain robotics team in New York, and performers is a new class of transformers architecture that Sepp has already mentioned in his talk. And the main idea is really to split the softmax attention matrix into two tensors for improving space and time complexity of the entire mechanism, as well as getting actually a more general transformer mechanism. It's a joint effort with several people from Google Brain, University of Cambridge, Google Research. So it's really was like fun to work on that. And the code of performers is also publicly available for those of you that would like to try it, or the results in the paper Rethinking Attention with Performers. So why we care about attention, memorization, well, in machine learning? I will talk about it more like from the robotics perspective, since I'm in the robotics team. At first glance, it seems that like in robotics, you don't necessarily need that much memorization, like lots of policies that you learn are purely reactive. However, if we think about lifelong learning, if we think about long-range navigation tasks, then immediately aspects of memory need to be taken into account, and how we can handle memory. That's why the revolution in attention-based architectures that was clearly marked by attention is all you need paper. It's something that, in my opinion, like will impact also robotics, even though we are like in a very early stage of that. And the angle that we take in Performers is to try to understand how we can improve the standard attention-based mechanisms used in transformers that are not very scalable. I will talk about it more detail, but space and time complexity is quadratic in the number of tokens. If you have a spatial attention, you can think about tokens as corresponding to different pixels. If you have temporal attention, you can think about tokens as corresponding to different events, different frames, like in the past. So you would like to have a scalable mechanism that can be characterized by much better space and time complexity. And you can actually even have a hybrid spatial temporal attention as it is presented here, where you have an agent with a camera, a bunch of frames. The agent needs to navigate, needs to memorize, think about the exploration task, but at the same time needs to distill from the image the critical parts of the image, critical patches or critical pixels that will be given to the controller to propose actions. And the regular attention mechanism is not very computational friendly because it's quadratic in the length of the input sequence. So it's not just about training, but like even assume that you have already a model that is well trained. You train for the week with the resources, like weak resources, but now you want to deploy on the machine with limited computational resources. Well, it's problematic right now to deploy heavy transformer-based models. So that's what we try to address in the line of work that we focus on. There are many different approaches to making transformers more efficient, making attention-based architectures more efficient, like with the most standard one, just sparsifying the attention. So rather than attending to everything, let's just attend to a local neighborhood, a local window like in the past, or even let's try to learn this window, but with some like big structure, I mean, very well-defined structure. In graph attention algorithms, the prior on the attention is given by the graph structure, by the topology of the graph. What we propose is the mechanism that will be characterized by linear space and time complexity of the attention model, but does not rely on this extra assumptions regarding attention. So you don't need to assume anything regarding sparsity, density, and you still will be able to benefit. So the key idea is that attention is kernelizable. If we think about the attention tensor, then we can actually rewrite it on as an expectation as a product of two lower ranked tensors. Let's call it Q prime and K prime transpose here, where you can think about it as the entries of the attention tensors corresponding to the kernel values. And those kernel values are given as expectation of dot products of certain nonlinear transformation of the embeddings corresponding to tokens or queries and keys. And those nonlinear transformations are usually randomized. That would be the case in particular for the standard softmax attention. So as long as you can rewrite the kernel values of your attention as an expectation of those finite dot products, you have a low rank decomposition. And the interesting thing is that you can actually do it for the regular softmax attention that is used pretty much like in most standard dense transformers. The very naive way of doing this decomposition would be through trigonometric random features. It's pretty much an observation that the softmax kernel that is used in transformers is inherently related to the Gaussian kernel. And we know how to find random features for the Gaussian kernel. And that really leads to the formula on the nonlinear mapping phi, defining the disentanglement given in this slide. This is not really the end of the story. This trigonometric formulation does not actually work in practice. I will talk about it a little bit later, and we'll explain how we can fix it. But let's assume that we have the decomposition of the attention matrix. Then the observation is that we don't really need to materialize the attention. We just need to have the action of the attention matrix of the given value matrix. So we use the decomposition of A, and we change the order of computations, matrix multiplication. We never explicitly materialize A. We get linear in L space and time complexity. Well, it also depends how many random features you need, but that's in a nutshell what performers are doing. Now, you can do the same trick in the causal for the causal attention. In the causal attention setting, tokens attend just to previous tokens. So it's really equivalent to taking the attention tensor and masking the upper triangular part. And it turns out that with the so-called prefix sum operations, where you keep the tensor of prefix sum of the outer products of the transformation of key vectors and value vectors, you can actually efficiently find embeddings of new tokens. So the nice thing about it is that the tensor, the outer product tensor sum, has shape which is independent from the length of the input sequence. So you can apply this mechanism in both bidirectional and unidirectional causal setting. As I mentioned before, that's not really the end of the story, because it turns out that the trigonometric mechanism for approximating softmax kernel does not really work in practice. And let me explain why that's the case. So what you see here is the 3D plot of the so-called utility function, which is defined as the ratio of the mean squared error of the trigonometric estimator in two given points, x and y, think about them as query and key, to the mean squared error of the new estimator that we propose in the performers paper that we called positive random feature estimator, that actually uses positive random features for estimating softmax. So those towers that you see here correspond to very large values of the MSE of the standard estimator, and this is the problem. So what's really going on is that if you want to estimate dense attention matrix with random feature map mechanism, there are lots of very small entries that you need to approximate accurately. If you use standard trigonometric approach, you will have a substantial variance of those small entries, and you actually want to be pretty accurate there. It's much more important to be accurate on many of those small entries than to be super accurate on large entries. The new mechanism that we propose in the paper has the property that the estimator is more accurate for the smaller values, and that's why ultimately when we do renormalization of the entire attention model, which is the standard important trick used in transformers, it just works much better. It's actually the only method right now that works for approximating the softmax kernel. And what you also see here is the slice of this utility function where we fix the length of the query and the key. Those asymptotic lines correspond to the settings where the softmax kernel values are very small. The values of the attention matrix are small. And this is where you want to be super precise. And the standard mechanism does not provide these guarantees. And yet, like another plot where we compare the mean squared error of the trigonometric mechanism and our positive random feature map mechanism in the region of small softmax kernel values. Now, this was like a little bit of theory, how this stuff works in practice. So what you see here is the plots benchmarking the time and space complexity of performers and regular transformers. And by the way, in one of the previous slides, I called this new mechanism that we propose a favor plus mechanism. So what does it stand for? It's orthogonal. So we use like a couple of different tricks. We use orthogonal samples in order to create estimators of the softmax kernel, and we use like random features obviously for the softmax kernel. So it's really fast attention via orthogonal random features and plus for positive random features. So getting back to this slide, what we see is that the solid curves correspond to the performer, the dashed one to the transformer, So you're running out of memory much later when you use a performer. On the x-axis, we have the logarithm of the sequence length. On the y-axis, we have the logarithm of the of time. Also, we see that we have much better time complexity for much longer sequences than the regular mechanism. The black curve that you see in last four plots here with those black crosses correspond to the, what we call it, a dummy transformer, where the attention is trivial. So the value vector is really, the attention matrix is really just the identity matrix. There is nothing really going on like with the attention. And the bottleneck really in terms of space and time complexity is in the MLP layers. So what we see is that with this new linear attention mechanism, you can actually match memories and time-wise a mechanism where we don't have attention at all. It basically means that the bottleneck now is somewhere else, no longer in the attention module, but in the MLP module. On the right-hand side, in particular, you see the comparison of the orthogonal mechanisms that I just mentioned. So in order to construct those random features, you use ensembles of Gaussian orthogonal vector versus the IID one in terms of the mean squared error, as long as the comparison of positive random features that we propose in the paper versus standard trigonometric ones. So the quick summary is that you would like orthogonality and you would like positive random features. That's the idea. One of the most important features of this mechanism is that it's backward compatible with the regular transformer with a little bit of fine tuning. So if you use like other standard fast lock mechanisms for computing attention modules, then you need to make sure that the training is also done with those mechanisms. You cannot just plug them in on the top of the regular softmax trained transformer. Now that's not the case for performer. You can actually do it. You can do inference with performer with the mechanism trained with the regular transformer. And this is really what this plot shows. Now, one thing that I want to emphasize is you don't necessarily need to use softmax, approximate softmax attention in performers. You can use any kernel you want. You can even use kernels that use deterministic finite features, and we will do it in practice. So it's a much more flexible mechanism. But in particular, as a special instantiation, it reconstructs the regular softmax attention. And now let's get back to, well, how it works in practice. So this is an experiment on the PG19 text data set where we compared a bunch of different transformers. And the stuff to take it from like this picture is really performers work better, much better if you have this new positive mechanism, positive random feature mechanism. Trigonometric features are not stable. And also you would like to withdraw the features that you use in performers periodically, just to make sure that you're not stuck in local maxima, local minima. Now, the point is that in this setting, you can actually run regular transformer. It feeds memory, and it provides like really a good accuracy. However, in the following setting that I present here, ImageNet64, we are talking about sequences of length 12K plus. You simply cannot train it with the regular transformer. So here we did comparison of performers and reformers, which is another class of transformer architectures that are based on LSH hashing. So this is a sparsification mechanism. And what we see is that we can achieve better accuracies. We can actually match accuracies of reformers with substantially fewer number of layers that we have in performers. And doesn't really matter whether we use a performer ReLU variant. That's what you see here. The ReLU really stands for the ReLU kernel here. We used ReLU nonlinearities to define the kernel, and we have deterministic features, or whether you use the approximate softmax variant that I was talking about a few minutes ago. Now, an area that we are particularly excited about is protein design. And the reason for that is that it's a great time for machine learning for proteins these days. And just a couple of days ago, we have heard about the huge breakthrough that AlphaFold V2 did, pretty much cracking the 3D structure of proteins. And as they say in the publicly available blog, they actually use attention-based architectures in this new mechanism that they propose. And we also applied attention-based architectures for protein modeling in our research, focusing on this efficient scalable transformers. So why the protein design is an interesting area? Because this is where you really want a long-range attention. Think about the protein modeling as a language problem. When different proteins correspond to different amino acids, and the amino acids attend to each other. And usually the 3D structure of the protein is defined by amino acids that are not necessarily very close in the primary structure, but tend to be like very close in the tertiary structure. So you would like to model these long-range dependencies, and that's why you definitely don't want to have local attention. You need global attention. Whether you need dense or sparse, it's a question, but you need something subtle. Now, original proteins are not that long. I mean, standard proteins are not that long. These are the results that we have for protein modeling in the unidirectional and bidirectional setting with performer, comparing with transformer and reformer. Those proteins here are, well, they have like a few hundred amino acids. So you can run the regular transformer for them. You don't necessarily need performer for that, but we wanted to see how the approximate mechanism compares against the compares like with reformer and regular transformer, and it works pretty well. Now, what is even more exciting is the complexes of proteins, and that's something that we, well, kind of like we did the proof of concept, really, where we stuck together a bunch of different proteins and tried to model them like all together. And it turns out that that's exactly the setting where you need much more efficient mechanisms. Because if you have like a protein like of like 1,000 amino acids, which is considered to be like a long chain, it's not a big deal for regular transformer. If you have like 8,000 amino acids, it's a different question. And if you want to use regular architectures, you need to substantially reduce the number of layers that you use in the mechanism, the batch size, etc. And that, of course, affects the quality of training. That's not such a problem for more efficient architectures like performers. And that's what we are very excited about, and we want to focus more in the future. Now, it also turns out that it's interesting to look into what patterns, what attention patterns those new efficient transformer architectures are discovering. So we had collaboration with the team at Google, led by Lucy Colwell, who is, I mean, they're like experts in bioinformatics, and they did for us this amazing pictures and some analysis of what is really going on with these efficient transformers in the bioinformatics context. And the interesting thing is that attention patterns look qualitatively different than for transformers, yet we are capable of recognizing highly similar amino acid pairs. And that is like really exciting. So that's an area of research that we would like to focus on more in the future. And the nice thing is that there is also a way to compare a bunch of new efficient transformers architectures that were recently proposed, in particular the paper Long Range Arena, where a bunch of different recently introduced transformers are compared, more and less efficient. And it's interesting to see that methods based on low-rank decomposition with random features or kernels mechanism in general work pretty well in that setting. All those evaluations were conducted independently by other researchers. So it's definitely, there is a room for efficient research with these new classes of architectures. Now really the question is what classes of problems you would like to focus on, where this very long sequences will play an important role, and then you can really leverage those architectures efficiently. And that's it on my side right now, and I cannot end this talk differently than just thank you for the attention. Thank you.
Thank you. That's been a beautiful presentation, and ending on such a nice closing sentence. Johannes, would you like to add something from your side, perhaps?
Yes. So now I have the honor to give a bit a connection between transformer, performer, and associative memory, like Hopfield networks. We've already heard in Sepp's talk how the transformer relates to Hopfield networks and what one can do with Hopfield networks. And of course, the obvious question is now how a performer would relate to Hopfield networks. And this is something which I looked into together with Hubert Ramsauer. And I will so quickly recap these concepts and summarize the talks we've heard today, such that we can start a discussion from that onwards. So maybe I should start with what Sepp was telling us about. So self-attention and modern Hopfield networks. By the way, I copied the very nice plots from Krzysztof. So all these plots are from the group of Krzysztof. So this plot here, for example. And so the self-attention was introduced by Vaswani in 2017, and we all know that transformers have taken the NLP tasks in Storm, but they're also now taking over in vision and in many other tasks. And well, the downside to transformers, as we heard, is that the complexity scales quadratically, meaning that for long sequences or many tokens, the order of complexity just gets too high. The basic principle is that we have this attention matrix where the keys and query matrices are put in, and the attention is basically the softmax over the row-wise softmax over this matrix product of keys and queries. What we have shown and what Sepp was talking about is that this self-attention update of a modern Hopfield network, which we introduced earlier this year, and which has this energy formula here, has an update rule which resembles the self-attention of transformer networks. And one can easily visualize that by having again the Simpsons characters from Sepp's talk. So what we have in the transformer, we also have now the keys, which are some stored patterns, a query, and the softmax helps to attend to the most important patterns, and after that we retrieve the pattern we want. So this update of modern Hopfield networks is really the transformer attention. And now we've heard this very nice talk from Krzysztof about performer. I again have this picture of the kernelized self-attention here. What performers are doing, as we've heard, they introduce this randomized mapping to decompose this attention matrix. And the very nice thing is that now this product of K and V is linear in L, and also the product of Q with the product of these two terms is also linear. Meaning that the complexity from the order L squared is now a complexity which is linear in L. And this has some really nice advantages, as we've just seen in Krzysztof's talk. But there are many other nice viewpoints from the performer. First thing is that the expectation, if you throw many of these random features, really equals the softmax, and but there's no softmax operation needed, meaning we can split these terms apart and we can first calculate the product of key and V. And by calculating this product first, we also can relate to some kind of Hopfield network, namely to a classical Hopfield network, which I will show in the next slides. Okay, so I tried to relate to the Hopfield networks, to the classical Hopfield networks first before going more into detail. So what the performer is doing compared to the transformer, it is not calculating the product of the matrices or tensors Q and K first and making the softmax over these terms, but first calculating K and V. So we can write here the term as W. So we have some expectation over a tensor W and the mapped Q. And if we write down this expectation value here again, and we write down the update of the classical Hopfield networks, which, as I said, I will introduce in the next slide, we have some really similarities again. So we have input patterns, these are the Qs, and in the Hopfield literature they are termed with Xi. We have some stored pre-computed storage, this W matrix, which is in the performer the product of P and V. In Hopfield networks, some form of how the patterns are stored, and then we have some squashing function. Hopfield networks, this is a 10H. In performer, this is this D to the power of -1. So we also have some close similarities to classical Hopfield networks. And I think I said now the term classical Hopfield networks a few times, and it's really time to introduce it properly. And I do it via having the modern Hopfield networks, which Sepp was talking about on the right side, and the classical Hopfield networks on the left. I've written down both the continuous versions because we are really interested in continuous patterns, because as Sepp said, we want to make everything differentiable. Both networks have of course, the aim to store patterns, and the patterns have a certain dimension, and L is the number of stored patterns. What's really different is how the storage is calculated. So the storage, which is denoted as W here. In classical Hopfield networks, it's the sum of autoproducts of all the patterns. So once these autoproducts are done, the storage is basically a matrix and can be stored away. In modern continuous Hopfield networks, the storage is really all the patterns. So for retrieving patterns, one has to access all the patterns individually. So one has to carry these patterns away. Here one already sees that the big difference between transformers, which are related to this modern continuous Hopfield networks, and performers, which are related to this classical Hopfield networks, where the storage is calculated and then can be accessed via the queries. Another big difference is the storage capacity. This is much higher for continuous Hopfield networks because it's shown it's exponential in the power of D. Whereas the capacity of classical Hopfield networks that's the very famous storage capacity ability for classical Hopfield networks with a small retrieval error. If we visualize these two concepts, we have the classical again on the left and the modern Hopfield networks on the right. So the classical Hopfield networks have this storage, multiply a pattern with the storage, and have a squashing function and retrieve a new pattern out of that. The modern continuous case is really all the stored patterns product with the input and the softmax, and they retrieve again a pattern. So this is the performer counterpart, and this is the transformer counterpart. And one always trades some kind of storage against computational cost, but it's not so. One cannot really say how much storage is needed for example, modern NLP tasks, because it not directly relates to the length of the patterns. And basically my last slide now, we managed to make the same Simpsons plot now for the performer part. So as I tried to visualize this breaking apart of the attention mechanism into first calculating the product of the K prime with V, enables us to give us some kind of storage matrix W, which is related to the outer product matrix of classical Hopfield networks, and which is visualized here. And then we retrieve patterns by applying the input patterns. So the input Homer mapped to Q prime with multiplication of this storage matrix. And the nice thing, as we've heard already, that in expectation the performer really assembles the transformer. So it takes the best of two worlds. It reduces the storage capacity, but it still manages to keep the properties, the intriguing properties of the original attention mechanism. And in expectation, the capacity of the performer should match the capacity, the storage capacity of continuous modern Hopfield networks. That's basically the bridge I wanted to show here between really this ancient concept of Hopfield networks, which are not so ancient anymore, this transformer architectures, and the very new and younger and smarter brother, as David said, the performer. And there are, of course, a lot of open questions which we are asking us, and that's why I put it here. Maybe there's some more, but this is all which came to my mind. So we were able to write down the energy function of continuous Hopfield networks. Is it also able? Can one also write down the energy function of the performer? What would be the properties of such an energy function? Like as Sepp told us of the retrieval properties, of the convergence properties, how would they relate to continuous Hopfield networks? About the capacity, we heard that we sample random orthogonal features. How does this number of sampled features influence the capacity of the performer? And the big question here is, does this capacity tell us something about the maximum sequence length? Or is it not really related? And for NLP tasks or for classical tasks, it's so the classical storage capacity is quite enough. One does not really know that. And of course, the one question is also, are there other ways to approximate the self-attention mechanism? For example, when Hubert and I played around with this performer analogy, we stumbled about sparseness, which is used in the classical Hopfield literature to very much increase the capacity. Can this also be applied here and maybe help to achieve some similar effects? That's basically all.
Thank you very much. I think we had a beautiful introduction to the exciting recent developments and open questions. I would like to invite the three panelists to discuss these points. And if there's any questions from the audience, please do write them in the chat.
Yeah, I think it's, yeah, maybe I will start. I think it's a really beautiful connection. We are pretty excited about it because I think it's kind of like it's a gateway to thinking about transformers models differently, right? I mean, one thing is that we can use all these different variants of modification that Sepp was talking about, and that may actually work much better in practice than regular transformers. Also, I think that in general, it's a very healthy way of thinking about transformers architectures, really about these attention modules as kind of like some sort of like dictionaries. So the question, like, what's the capacity of your dictionary, how many patterns you store, because that's kind of like in some of our experiments that we conducted, like we observed that this is pretty much what those attention blocks are doing. Like if you read kind of like standard tutorials on transformers, and there are like, I mean, probably hundreds of thousands of them like in the web, you know, the story usually is, well, you have the attention and you kind of try to create those linear combinations of the valued vectors corresponding to the tokens, which somehow like tell you like how relevant like you are like to the to other tokens. But what is not really clearly stated is that well, the module can actually act exactly like as a dictionary, and those patterns can be restored very efficiently because of this convergence result that Sepp was talking about, right? Like when you have like extremely fast convergence, so you don't need like many steps, right? Like even of the attention module, and I think that so stuff that I'd be like really, I mean, interesting theoretical question, right? Like to answer is, if we take this the performer version, so the performer version, if we can think about it as we do linearization where there's like no linear transformation at the beginning, then we can linearize like everything at the end. what can we say, right? Like about the capacity of the dictionary. I mean, it should be worse than for the regular transformer, but the intuition is that it should be still much better than the classical Hopfield networks. So what can be like theoretically proven about it? That sounds like a exciting question. So a couple of very introductory comments at the beginning.
Yeah, and also an interesting question is how this capacity really relates to length of sequences to number of tokens, because this is not so clear. And for sure, so we have in the classical Hopfield literature, there's tons of research on how to increase storage and increase the capacity by, for example, as I said, making networks sparse. And the question is, does this help? And would one go into this direction? For example, make transformer models more efficient? Yeah. I think this is a very interesting line of research, because it's more and more getting important to be compute efficient and to be able to store more and yeah.
Yeah, exactly. I completely agree. Regarding this sparse patterns, right? The interesting synergy there is that you don't really necessarily even need to use the softmax kernel. You can use different. If you think about it from the performer point of view, you just use some kernel for which you find the decomposition. And we actually tested, that's what I mentioned in the talk, performer ReLU variant, yes. And observed that surprisingly, in bioinformatics applications, it was often substantially better than the regular transformer. So that was very intriguing. And the question is really, what are those right attention kernels that should be used? And I'd be interested to see whether we can get some insight into that through this kind of thinking about from the dictionary point of view, capacity point of view, the angle of Hopfield networks, because that's, in my opinion, an important question. The way how I think that the original transformer architecture was set up is that attention models were known for a while. I mean, long before transformers were proposed, and people kind of step by step tried to put together different blocks, and yeah, there were lots of heuristics skip connection here, not there, do some type of layer normalization, etc. But I think the interesting conclusion from this kind of relationship is that there is a much more rigorous way of thinking about it, and elegant from the mathematical point of view through the lens of memory of Hopfield networks, and then it's possible to potentially get some provable mechanisms, get extra insight about why this particular variant works better than the other one. And I think we need it in the field, because training transformers is just difficult, and I know it from my experience. I mean, we have computational resources at Google, so somehow, I mean, we are lucky that we can run those large models, but it's hard. I mean, running ablation studies over what types of kernels you would like to use, or kind of how to connect these different pieces. It's problematic. That's why, in my opinion, we need extra theoretical insight to understand better really what transformers are doing, and that's, in my opinion, a step in the right direction, an important step.
A comment to this, Krzysztof, what you're saying, I completely agree. But things are even more complicated. You use some of the kernels. We think about the capacity of the dictionary, but these architectures learn. They can also learn to exploit the particularities of these kernels you're using. Perhaps they go into a subspace where you particularly perform well. We have this dictionary module, but we also have some mapping into this dictionary module, and therefore also the outcome is further processed. Therefore, this interplay of this makes things even more complicated, and it's hard to understand. Perhaps you use a not so good kernel, but then it learns to exploit this kernel and use it in a right way. And this interplay is even more complicated.
That's true. Yeah. Yeah, and I think like since we are talking about this connections, Hopfield network transformers, I do think that you know, this is so when we talk about applications, right, and in particular where this like new Hopfield type models can be tested, it's in my opinion like bioinformatics is like one of the, for me personally, the most like exciting one. Because you can really, I mean, you know, what is more natural language, right, than the genetics, right? It's the most fundamental one, and if we talk about this, then transformers have been like people start like using them in bioinformatics, and attention-based models are used. I mean, that's what AlphaFold is. We don't know exactly what is like behind like the algorithm, but they use attention-based models. As they admit in the blog. So there are lots of settings in bioinformatics where you need to deal with much longer sequences, and this is like when I mean, it's a great opportunity for transformers. Like we already have a signal that they make a huge difference and outperform like standard like mechanisms. But I also like do think that that's the place like where this modern Hopfield networks and all these different variants that you are proposing can be used successfully. One very specific thing is complexes of proteins, right? It's kind of natural step like forward, like from what AlphaFold did, right? Like instead of just like mapping, right, like a 1D structure into the 3D structure, position of the carbon atoms, etc. Let's take those complexes and let's try like to do the same stuff. And then suddenly lots of brute force approaches don't work. And that's also like an opportunity potentially for this kind of like more efficient models. And I really like, I truly love this. I think that like in a nutshell, right, like what is like very elegant, right, like about this relationship is that, so if you use classical, that's what Johannes mentioned. If you use classical Hopfield networks, the dictionary, the size of the dictionary is independent from the number of patterns that is stored, and that's beautiful about it because it's compact. Now, of course, the price that you pay for that is capacity. Now, in the performer world, this dictionary is this the sum of this outer products, which is like of shape m times d, the number of random features, times the dimensionality of the embedding, times like some batch dimensions, which is completely independent from the length of the input sequence L. And that's exactly, you know, that this like relationship there. So as a robotician, I'm kind of like excited about it because you know, we want to deploy those models on real hardware, and I cannot imagine our robot like in our lab like in New York like running like on the like full transformer model. We would need to do something much smarter. So yeah, anyway, that
Krzysztof, because you mentioned biology, perhaps you thought about also medical application. If you look at the DNA is a very long sequence, and you might have mutations, you might have SNPs, stuff like this, and they interact, say, on different places on the DNA. But then proteins are produced, and the proteins see each other. Therefore, you have to interconnect different positions on the DNA. Did you think about stuff like this? It would be for understanding diseases and stuff like this, genetic preferences. Perhaps this would be a good application. And there you have really long sequences.
Oh yeah, yeah. This is actually perfect, right? Like genomic data, because I mean, just to give like all the viewers, right, like some perspective, right? Like when we talk about proteins. It's about like few hundred amino acids per protein. If you have like 1,000 amino acids, it's considered to be a long protein. Of course, we can go to complexes, but individual proteins are pretty short. Now, if we talk about genomic data, if you take a genome of the HIV virus, it's about 4,500 units. If you talk about the honeybee genome, it's about 250 million base pairs. And if we talk about the human being, it's about 8 billion, if I remember well. So this is like the setting, like where you need like a little bit different tools. Like you just cannot go brute force. And as you said, right, like it's, I mean, understanding the mutations, understanding the non-coding regions in the genome, like what they are very often responsible for diseases. This is like of huge importance in biology. So this is a good time for new technology in machine learning to just step in and show its relevance.
What I also bring up, I already mentioned it in my part. What we did until now with deep learning is a lot of function approximation. We have an input, we have an output. But I think for going the next step, perhaps that's not sufficient. We have to enrich our processing with context. Context from everywhere. And we as humans, we are probably not function approximators. We always live in the world, live some context. We have some memories, have some associations. We always connect everything with everything. And I think that could be a good way to tackle new problems with things like transformers, performers, perhaps Hopfield networks, where function approximation is enriched with other information which is collected, perhaps from the previous layer, perhaps from the outside, perhaps from a different sensory input. I think this has a rich future in the sense that you can build architectures where you can integrate different data sources, you can integrate intermediate results, you can go back and reanalyze stuff after having your first results, all this kind of stuff. And this is a huge opportunity to come up with complete new neural network architectures.
Yeah, I completely agree, and I think that in particular, you know, this can be like nicely showcased in robotics, like where think about the lifelong learning problem, like where you really want your robot to take the as much signal as possible. You make it like a vision, like input. You would like to attend over time, but since the visual input is also very rich, you need to distill the important information, right? Like the way, like how we process like information as human beings, like we distill the important. We don't need like every single detail of the input that we get like through our eyes to make decisions, to make actions, to propose actions. And so how this distillation can be done with attention methods, where you need to, so there are like different levels, like where you can learn how to attend. And that's why like robotics is particularly relevant here. And also the other interesting thing is if we talk about this lifelong learning, there is lots of combinatorial problems that need to be solved. They require memory. You need to do accomplish certain tasks. You need to like build like in a particular order. You need to memorize. So this kind of like the connection, the synergy between the combinatorics of the problem and memory is also something that in my opinion is like very interesting and not really handled well by current solutions. I mean, we are really very far from processing this like data in an efficient way, the way, I mean, by robots, like the way like how human beings are doing it. So it is like an opportunity, you know, we need to learn how to process this rich signal. And yeah, transformer like networks, attention-based architectures, like in my opinion, like will play an important role. But also like what I think is that we need algorithmic breakthroughs. Like we need like to have like also like deeper connection like with other fields, in particular Hopfield networks, to better design those architectures. I don't think that I remember when I myself like learned about transformers at the beginning. It was like for me the very first like observation, a bunch of hacks. Like you put attention here, you put skip connection there, you do some layer normalization. and it just miraculously works. And that's why I really appreciate this Hopfield network point of view, because that kind of like gives a much more rigorous intuition. And I think it's important, like for people that don't want to just blindly apply it as a black box, but really want to modify and improve those mechanisms, especially in the context of robotics.
Krzysztof, you mentioned lifelong learning and this kind of applications, but then perhaps you need mechanisms which decide what put in your dictionary and what remove from your dictionary, or perhaps what combine in your dictionary. You need a new mechanisms, I would guess, to keep the memory stable, or not that everything is averaging over everything. This could be also ideas for coming up with new ideas. I did this once on LSTMs. We have this gating mechanisms. Perhaps things like this also make sense. What should I store? What should become keys, and what things I already know and would not put as keys into the memory? Stuff like this. I don't know whether there's research going on in this direction, but for me it would make sense.
Yeah, I mean that's something that I would say, like, you know, in robotics, like we really just have started appreciating those concepts because of the revolution that is happening in supervised setting right now, where we pretty much like almost like, you know, every week we have some big news. And you know, like there was like a big news about transformers, new architectures outperforming CNNs. Actually, like maybe it's a farewell to CNNs. I guess that's probably like will be the case now. Well, we have like AlphaFold, where we know that attention-based architectures are used. We don't know how, but we know that they are like already applied, and it's a game changer, because they went like from, they get like 90% plus accuracy right now, which is pretty much considered to be a solved task, even from very challenging proteins like this SARS-like proteins that were really hard like to model before. So and this revolution, like in the supervised setting, somehow like you know, comes like to us, to the robotician world. But yeah, I agree with you. In some ways, in robotics, it's even more difficult. There are lots of like other questions that need to be answered. And what those queries and keys would be: how to well refresh this memory, how to get rid like of the old memories. We don't know how to do it, right? It's just like we are at the beginning of the road, but that's why it's pretty exciting time.
I completely agree, especially there's so much open right now, and also with your research, you brought also new ideas, new insights, and also you created a floor for other guys to build new architectures on. I think it's a very rich field in this moment.
Yeah, I think we are like at the beginning of like something like really exciting, like research-wise, and it's exactly an opportunity for lots of people to step in with their own ideas, like look at the connections. For me personally, what was very exciting to see is that you know how and well, I'm kind of like I have like a very mathematical background, so I'm a robotician, like with a very theoretical background, which is maybe like a little unusual, but I like it, and I like to leverage it when I can. The nice thing that I observed, like when I work about on performers, is that those nice mathematical elegant ideas actually turn out to work in practice. So you don't need to really do just like some type of like heuristics, like and I will give an example. So when we started working on performers and we realized that you can decompose the attention matrix using random features. Of course, the first approach was let's use Gaussian random features, because we know how, I mean, trigonometric ones for the Gaussian kernel. And our first approach was with trigonometric features, and just didn't really work well. And I remember us like spending like weeks on that, and it just didn't work. So it was like, okay, it's a nice, elegant like idea, but yeah, unfortunately, there are some like issues like in practice. And then it turns out that there is another way of constructing those features using exponential mapping that provide us these positive features for the first time. And then we realized, and that was like really exciting time, is that the orthogonal mechanism that we knew about for quite some time works particularly well with them. We managed to prove certain results regarding the accuracy of the estimation of the softmax kernel by combining the orthogonal mechanism with these positive random features. And it worked much better in a sense, also like from the purely theoretical point of view. We could get like lots of results showing that the variance is smaller, the concentration is better, not just asymptotically for large enough dimensionality of the embedding, but actually for any dimensionality D. And we heavily leverage the fact that the features are positive. So that was something for us, you know, very, very exciting, because it just shows that, yeah, this kind of like mathematical intuition is very useful here. In the field that you, at first glance, you would think like it's highly practical, and kind of like people like look into more like empirical aspects and are driven by experiments, rather than kind of like some mathematical principle. But actually, you can use mathematical principles pretty effectively there.
I have to also tell another application. I don't know whether I'm allowed to tell. It's about interact design for synthesis. And here's this techniques have fantastic results. We did not publish until now, because you have a molecule, and now you want to predict how to produce a molecule, how to synthesize it. And the problem was sometimes you have a molecule, but you have only one molecule, and you have only one template, one synthesis template, and it was not solved. We used this Hopfield network idea, and wow, it works, because even if you have one as a template in your memory, if you have one molecule which is similar, you look, some molecules are similar, and you use a template, modify it a little bit, and then you can produce a molecule. And it was thought it's impossible that you learn from one thing, but with this modern Hopfield networks with attention, it's possible, because you can do both. You can look in the memory, is the one example, but you can also average over example, or do it. You have both worlds. You have single examples, and you have where you learn something like a rule. You can combine your rules with outliers, single cases, and this gave fantastic results. And so far, I think the field is open for many, many new applications.
Yeah, and this is like, you know, what really touches this, like, I mean, holy grail of machine learning, right? Like how you can learn like with many fewer samples, right? I mean, the standard models are just so sample inefficient, right? And it's this question, like how it is. I mean, I have like a small daughter. She will be 8 months old tomorrow, and it's amazing like how much she learns like every day. We try to expose her like to as many samples like as possible, but she's there with us like in the house, and she manages like to generalize this like from this like small sets, like learns the rules of gravity, etc. And so yeah, I completely agree, right? That next like revolution, right? Like in machine learning, like we require this memory techniques, right? Like where you can generalize from a couple of samples or even one sample, and you can like memorize. You can figure out what the outliers are. I mean, there's like a big field, right? And one-shot learning. There was even a paper recently, like 0.5 shot learning. That's kind of like the time where I think like those methods are needed in order like for us like to make the next big step.
I completely agree. Few-shot learning would be one great application where you store experience, and now you can transfer it very easily to other tasks, other problems.
Krzysztof, I have a question to you, because
sure.
What you tried is you replaced the softmax by some expectation.
Right.
But in the end, it turned out that ReLU might work best. So what do you think is the future to come up with new ideas to replace the softmax, or to better ways to approximate the softmax, or will the softmax be maybe completely replaced by some other clever mechanism which is not so compute efficient? Because like that your final performer module, which works best with Railus, is already going in some kind of direction, a bit like from replacing softmax.
Yeah, so yeah, very good question. That's something that like we try to understand better right now. When we started the research on that, we were told that you cannot beat softmax. Softmax is the best, like it's highly optimized. The reason why softmax is used like is that, I mean, researchers tried a bunch of different other variants and just the way to go. But we kind of like we're not like discouraged by that, and yeah, as you mentioned, like it turns out that in practice you don't even necessarily need softmax, which is also like an advantage, because if you do approximation of the attention, well, you still like need like random features. I mean, there's extra projections for the approximate softmax. If you use like, let's say, deterministic approaches, then you even don't need those like random features. So it's kind of like it's just like even simpler. Now we still don't really understand like where those other mechanisms are better. There's not like a clear like image there. We run some ablations over different kernels that that can be used in attention, and kind of like very initial results, they show that we definitely, so if we talk about this kind of kernel like point of view, then you would like to have positive features, because like negative features like are problematic when you do normalization. I mean, in particular, you don't want your partition function to be negative or close to zero. That's problematic. Also, you don't want your nonlinearities to grow too fast, because well, then you need to kind of like renormalize the entire mechanism in order to not have problems with numerical instability. We actually did it like successfully for the approximate softmax, that is using exponential mapping, but in general, it kind of like requires like extra effort. In terms of you know, other directions, right? Like what I was like thinking about is the idea of instead, so that the standard way, like how the softmax well, attention like works is, well, tokens attend to tokens. You can even, you know, really think about it as from the graphical network point of view, where you have like a graph, like different nodes correspond to different tokens, and well, either you have some structural graph prior, that's like what would be like the case in graph attention networks, where you just attend to your neighbors, or you try to attend to everything, or you learn your attention, learn some sparse attention patterns. But I was like also like thinking like whether what about the hypergraph approach, like where the relationship are not like really measured by pairwise relationship, but you have like sets of nodes. You kind of like want to like understand how the token like corresponds, the context like in the in terms of sets, like rather than edges. And then it's kind of like really a hypergraph approach, and what this hypergraph approach like would really mean in the context of like efficient like mechanisms, I don't know. But these are like some of the ideas that that we have in mind. So that's kind of like, you know, like another class of approaches. If we talk about you know, get back like to softmax, there are a couple of different ways of approximating softmax. One way is what we do in our paper. There is another approach in some like older papers that were using, they were projecting not queries and keys using random projection, but I think like keys like and values. And you can actually approximate softmax too, but in a biased way. So if you want an unbiased mechanism, then I don't know really like anything better but projecting queries and keys. Of course, there is a big question about sparsification. That's something that, you know, we were discussing in the team and with other researchers, because when we started working on performers, you know, the first set of comments that we get is, well, why you do it, right? There are like lots of sparse methods, like in the sense that you kind of like do some like type of clustering in order to reduce space and time complexity. And this is interesting, like the question, like whether those approaches, they definitely help, and there are lots of like very good algorithms. that in particular reformers that achieve like really great like results with these approaches. But the question is like also like what are the limitations of the approaches? So that's like something that I think like it should be like investigated more like in the future. In particular, in such applications like bioinformatics, the big question is, do you need a dense mechanism or not? So I showed the plots comparing performers with reformers, where we have substantial gains coming from not sparsifying, like from the dense mechanism, not doing hashing. But to be honest, like we don't know like whether what's going on is, well, the fact that we just need dense attention, or maybe the reversible layers that are used like in reformers have some like negative like impact potentially on training the biological models. Also, in terms of like the clustering approaches, I would say that you know, like one thing is, so this is a prior, like you assume that you can cluster like your data into chunks, and you will attend just like within chunks, but not between chunks. If you have like attention patterns, like where you cannot really do this, so you have like lots of like important pairs, but they're really spanning like the entire graph, then if you do clustering, it doesn't matter whether you learn these clusters or not, well, you will lose certain connections, important connections. So now the question is like in practice, right? Like, is it the case or not? We don't really know. So I think that in terms of like other ways of approximating softmax and attention, I think it's also important question to understand better the relationship between the dense methods used using low rank approximation. In particular, it's not just performers. There are a bunch of other techniques. Another one, I'm sorry, I'm just, my computer went crazy. I tried to wake it up. Let me see. Okay, perfect. I see you again. Another, in terms of other approaches, leanformers, for instance, right? Like another like a prolific class of algorithms that is used, representative of the low rank approximation approach. What's the relationship between those techniques and sparse techniques? I also do think that's kind of like additional comment is that those techniques, lots of them can be combined. They can be put together. And in particular, we already actually apply reversible layers from reformers in performance architectures, because performers are really just touching the way the attention is computed. But the MLPs modules can be computed in many different ways. So we can, in particular, reuse reversible layers that are pretty effective in many applications of reformers. So I think that like future research like should also, so researchers should be kind of like more generous, like in terms of like other techniques like that are discovered by others researchers, especially in the transformers field, when we have like so many like different types of algorithms. And just join efforts in order to come up like with efficient classes of attention modules. But in a nutshell, like the question of the best approximation of the softmax, it's a big open question. And very last comment regarding this. We know that the positive random feature map mechanism is provably and empirically better than the trigonometric one. Now, there is another question. Can we come up with something even better? Why I mentioned this? Because the nice thing about the trigonometric mechanism is that, like, even though the features are potentially negative because you use trigonometric functions, they are bounded because you use, sine, cosine. And boundedness helps a lot, like when you do analysis of this algorithm in terms of getting concentration results. When you have unbounded features, it's much harder to get this stuff. So an open question, it's like a very, maybe there is a simple answer, but like to everybody that is kind of like listening, is there a mechanism for approximating softmax of Gaussian kernel with positive random features that are bounded? That would be perfect. I don't know any. I do think that if there is one, then probably like will work much better than our favor plus mechanism, but I have no idea how to construct it. I don't also know how to prove that it does not exist.
Yeah, thank you very much. And I think sparseness was mentioned again a lot of times, and you do use ReLUs in which works.
Yeah, so they are like, yeah, so sparseness, yeah, it's kind of in a couple of different contexts. We can actually impose sparseness also in this, well, I call this dense, like low rank approaches, simply by taking a particular nonlinearity, like a ReLU function, where we sparsify like with the ReLU. And there is a whole other class of techniques, which are very prolific techniques, are actually like very successful, is to kind of like learn where to not to attend to, like which edges, like which they should be like taken away from this computational graph, doing either hashing or clustering, and this is like yet another like class like of techniques that you know, it's interesting like to understand like the relationship between this and the low rank decomposition methods. But yeah, I mean, it's definitely another like important set of tools that that should be considered.
Totally agree. Yeah. So I think you opened the field, and there will be a lot of research, and it's not clear where it is going, because as you said, or as Sepp said in the beginning, it might be that just applying some activation function like ReLU make the net learn something else which we do not think of, and there might be some surprises around the corner which follow directly in this line. So yeah.
And I do think that, you know, it's still like we are waiting like for we are still what we have right now in terms of this transformers architectures is still not the final target, what we really want like to have. There is still like lots of stuff that can be improved. I mean, transformers are not like very computationally efficient. We know it. There are lots of improvements like performers. So these are like steps like towards like better efficiency, space and time complexity to make those architectures like really usable, like for, you know, people that don't necessarily have computational resources that are available at industrial centers. And I think that there's the work that needs to be done algorithmically there. It's not just like putting more TPUs and just keeping like fingers crossed that that you know, like something like will happen, but the algorithmics like needs to be rethought, and that's why this angle, like this connections with Hopfield networks are just priceless, because they give us like important way of thinking about it from the algorithmic point of view. That's what the community needs, in my opinion, right now, rather than just like putting like more and more TPUs.
Yeah, we were really surprised when we saw that this could really be viewed as classically Hopfield networks, because when we tried to come up with all this continuous Hopfield stuff, modern Hopfield networks, it was like classical Hopfield networks are like 30 or 40 years old, and now we see one of the hottest new algorithms, and then one can really see really clearly this is an analogy. So it's really fascinating. But
it's amazing how those techniques, like the older techniques, are kind of like they turn out to be like useful, and they come back after like a while, and people just reuse them.
I noticed. I had also one thing which come much later now, but I think we have some questions from the audience, David, right? Yeah.
Yes, we do, but I just didn't want to interrupt your super interesting discussion. So, but perhaps this adds us inspiration. So we have four questions here. The first one is by Sunanda. I'm sure I will pronounce this wrongly. Gamaj or Gamaj. How does the idea of memory units in neural net layers that you're proposing compared to the neural Turing machines by Graves et al. Or to memory networks, Weston et al.?
So first ideas, I think the memory networks used instead of the softmax, I used the argmax. First of all, it's differentiable, but also these techniques already had differential procedures. But the important thing for me is it's readily be integrated in each layer of your deep learning architecture. You have a preferred architecture and you equip it only with some memory at this layer or that layer. You only have to think, what are the queries, what are the memories. It's not a specialized architecture. It should be out of the box architecture where you say, perhaps at this layer, the computation can be enriched by storing some previous results or getting something from the outside. And the memory networks, they are constructed architecture only for this memory. Here, the memory should come easily as additional processing. Therefore, I said it should be for each layer, you should be easily able to equip it with memories. You only have to think what the queries and what are the stored patterns. And the other architectures were designed for constructing only one memory, not a memory in each layer.
Thank you very much. We have 3 questions by Alexander Schim. So I guess I will do them one by one. His first question is on Hopfield networks. And he says it was very interesting to see your analysis on the equilibrium behavior. And he says that he thinks the analysis were done for individual attention with the same weight matrices applied repeatedly, and that the keys have to be kept the same, whereas the transformer output will create new keys. So his question then is, how does this limit or does this limit how the analysis describes how the transformer sublayer is transforming the hidden states?
It's true, it was only, the analysis is only for one attention head, this fixed thing. And what we say, what we see in the transformer or in the attention is just one update. It corresponds to one update of Hopfield network. We don't do a multiple update with the same keys. Whereas the output of the head would go into the input again, and we do another update. This will be the iterative update. We only analyze this. We said one update of one head is one Hopfield update. We didn't look into combining multiple heads. We didn't look into doing the output of one head into the next layer, because that would be a different Hopfield network. A Hopfield network would be only at one layer at one processing time.
Okay, and he follows this on by asking the parameters that the Hopfield networks learn are weight matrices, making them harder to interpret, he suggests, because it's easier to assume you'd already have keys or queries. And also he wonders how to interpret multi-head attention, where attention outputs are concatenated and linearly transformed, as well as the FC layer after that. And he's then asking, is there an idea how composing these 3 is moving around the hidden states?
Oh, that's a hard one. For us, each head would have its own energy. First of all, the interpretation of the weight matrix, what they really do, we don't have an interpretation right now. We only see after the patterns after the mapping go into the dictionary, as Krzysztof said it. But what this is doing is not clear. Perhaps they're already unifying some different patterns to one pattern, which is then stored. I don't have an interpretation for that. More interesting, I think, is if you have different heads, because every head has an energy. Can we combine this energy? I don't know. Perhaps we have to ask physicists or stuff like this. Yes, there are different energy states in one network. I don't have an idea how to combine it, but perhaps it's possible to compute something like a combined energy or something like this. I don't know.
Mm-hmm. And then he has a last question, saying that this is actually more his focus of interest. He's wondering, have you looked into a probabilistic interpretation of modern Hopfield networks or transformers, and connecting that to the optimization framework laid out in the paper. Log sum X is used a lot in convex optimization, but it has a distributional interpretation like Jane's derivation of maximum entropy distributions over a discretized space.
There are two ways how to do it. First of all, we have in our framework something which we call a beta, and it can be interpreted inverse temperature. And if we calculate it through, we can derive something like a mixture of Gaussians. And here, the inverse temperature is something like the uncertainty. It's a covariance matrix. Therefore, beta directly relates to the covariance matrix after some computations. Another way where we looked at is the log sum X is also the Legendre transform of an entropy of the Shannon entropy, and coming from this direction, but this would be more the direction of the convex optimization techniques. The other thing, the probabilistic interpretation would be via this beta, which is inverse temperature, and you have with a small temperature, you have a very precise or very large likelihood, and with a low beta, high temperature, you are unsure, you have a low likelihood. If this output is transferred into something like a mixture of Gaussian with likelihood or density, or if you compute the likelihood actually.
Thank you very much.
One thing that I will just add on the top, what I think in terms of this like Hopfield style interpretation, the most important is that you don't need to have like many updates like to converge to this equilibrium, right? Like you have like with this like new energy function, you can actually like do really good stuff with one update, which is like really, so you don't need to like many times like apply like this like a particular attention. So it gives you like a really good interpretation what's going on in the attention module. Now transformers is bigger than this, but needless to say, right, this is like the attention which is critical for all the revolution that is done in transformers. So I think that this dictionary point of view is like a very healthy way of thinking about it, and that's what's like given in this Hopfield interpretation, and it's pretty like rigorous mapping from the attention to this one-step update, like with this new efficient function corresponding to the exponential capacity of the dictionary.
Completely agree. Absolutely right. Do we have further questions, or I don't know?
Well, I don't see any further questions in the chat right now. I just wanted to say thank you very much for this fantastic discussion. If I may be so selfish, maybe I can add a few thoughts of my own. I really appreciated also the handle on the learned attention, trying to interpret that. Like when you compared the Blossom 62 matrix with the learned similarities from your bioinformatics application. And I was actually wondering, in the context of transfer learning and multitask learning, to what degree this built-in understanding of the world that's encoding in this attention can actually be transferable. Because in classical bioinformatics, this matrix comes from a single task, which is looking at the conservation in evolution of similar sequences, and based on that, you would expect the isoleucine to be more similar to the valine, because that's the most frequent exchange you will find, whereas your learned attention shows exactly the opposite. It's qualitatively different, assuming that the leucine and the isoleucine are more similar. And that I think is really exciting, because perhaps in this context, that's the correct answer. And then the question is, what does amino acid similarity actually mean? Is that task specific? Can we learn something more generic about the use of amino acids, maybe in the context, as Sepp mentioned, drug design? Maybe if we have a particular application in mind, a different understanding of amino acids would actually be much more appropriate. So I'm really excited about that. Do you have any thoughts regarding interpretation of these learned attentions?
So we still don't. This is like a big open question, and what I think is we still try to understand what's the best way of using attention-based models for protein modeling, because if you think about AlphaFold point of view in the algorithms that where they use attention, this is pretty much like learning the positions in the Euclidean space on the atoms. Like the protein backbone is important, but I guess with this 90% plus accuracy, they probably also very accurately, they needed to accurately estimate the positions of the atoms in the side chain. However, the other approach is to go directly to functionality. It's kind of by passing this 3D structure. Also for the reason that the mapping from the 3D structure to the functionality is still very, very non-trivial. It tells us, of course, a lot, but I mean the topology, the tertiary structure, but it's still a question how we can leverage it in the best way. So this is something that is on our plate, to understand better. What we figure out is that with performers, these attention patterns that we learned for amino acids were kind of in some way more not concentrated just in a couple of regions, but kind of more prespread out around the entire matrix. However, they also saw a bunch of other patterns that were quantitatively just different, not present before. So we still need to really understand what is going on there, and I do think that it will be important if we go to applications when we have much longer sequences, like genetic data. And we try to do modeling and understand the functionality of different sequences, non-coding sequences of the genomic data in terms of particular diseases. Then yeah, I mean we will need to have extra insight into what's really going on there. For us, actually, it was really fun to see that when we entered this area of efficient transformers. At the beginning, we didn't have an idea that bioinformatics might be an application for those type of techniques, and just discovered it and learned bioinformatics in a couple of weeks. But we have an amazing team of real experts at Google that just did amazing job to make our life as simple as possible regarding learning this concept. So yeah, this stuff is something that, in my opinion, it's probably the most important in terms of well, applications that we human beings will benefit from in the hopefully near future. So yeah, still more questions than answers, but yeah, that's how science is.
But that's good. So both you and Sepp mentioned DNA. I mean, if you're going to look into DNA with the 3 billion nucleotides in the human genome, or if you look at even the thought that maybe it's not even enough to look at single chromosomes. I mean, if you look at circular chromosome capture, you see that they interact even across chromosomes. So there you really need this global view, but yet again, you will only find a handful of relevant interactions, like say 100 to some maternal imprinting location. So that directly brings us back to sparsity that you've been discussing so much already. Do you see a natural mechanism that into the current models? Would that go through the energy, or how would you do that?
Yeah, so on the so from my point of view, yeah, it's a natural setting where you need either to use sparse attention methods, or these low rank attention methods where you can still like model dense attention where you don't put any extra structural priors, but you are much more space and time efficient, because we need this efficiency. We need to model long range attention. Now, whether having extra priors like coming like from hashing clustering techniques would be harmful or not, we really don't know. To the best of my knowledge, I think like so far in the bioinformatics field, I might be wrong, but like in terms of this efficient transformers, these were the performers that were really applied. I don't know, we ran some experiments like with reformers, but I don't know like any effort on doing exhaustive like comparison like of different sparse methods and comparing like with low rank attention. So we really don't know. I think that the fact that we have mechanisms that don't need to put any other structural priors regarding attention and are capable of modeling long attention with much better space and time complexity is important. However, since here we are talking really about long sequences, I mean, 8 billion amino acids, 20-something number of chromosomes, interactions on really long range, it might be the case that what we need is a combination of several methods. So even if you take like the performer, it's linear in terms of the length of the input sequence. That's if you want to apply it brute force, that won't be enough like for the genomic data. So you need like to add like extra techniques, and it's a natural test bed for combining like a bunch of them, where you can do sparsification using a bunch of different algorithms. And then within each cluster, it can be still much larger than normally you can apply low-rank techniques as performers. So that's just like a wonderful like application, and exactly like we need this new algorithmic concepts. And I would say like it's even more important than like in protein setting, because yeah, it's billions of nucleotides instead of hundreds of amino acids. So you really need something else. Yeah.
Yes.
Thank you very much. Well, if there are no further questions, let me thank you again for this amazing discussion. I really enjoyed it, and I learned so much. And you've pointed out that despite all the exciting things that your recent scientific publications have achieved here, even more exciting steps are ahead. And I very much hope that we can discuss again maybe next year what has happened along the road. Thank you again for your contribution, and thank you for joining us.
It would be amazing to have some breakthrough like for the genomic data for the meeting like in the next year.
Great, fingers crossed. Thank you again for joining us, and have a good night.
Okay.
Thank you very
or a good day.
See you again.
Bye.